Thanks. So I'd like to thank Andrea, Ashraf, Cyril, and Jean-François for the invitation and for accepting to move my talk on schedule because I was supposed to speak tomorrow, which is also the reason I apologize with you because you will have a second long talk today. So the talk of today, so my talk, will be somehow different with respect to many other ones we've had here at Mathématiques, which we are focusing on probabilistic numerical methods for high-dimensional problems or for their mean field limits. I would rather focus on the problem of finding exact approximate solutions for low-dimensional nonlinear problems, and precisely the nonlinear PDEs that appear in optimal stopping. Okay, so it will be somehow orthogonal to the direction that many talks had until now. So my motivation comes from mathematical finance, okay? So this first part will be maybe somehow obvious for some of you, but hopefully not for others. So the motivation is the following. In mathematical finance, we have a stochastic process that models a financial asset, okay? A stock, let's say a stock, so the stock of Google or Société Générale, for example, where my co-author works, okay? So what we say is that this is a price, okay, expressed in euros of Société Générale stock, and we model it with an SDE. Okay, so WT is a Mariner motion in dimension 1. Oh, and by the way, what do I mean by low dimension? Once a colleague of mine said that high dimension starts from d equal 2. And so by contrast, low dimension will be d equal 1, right? Okay. Brownian motion dimension 1, and sigma is a function of time and space with values possibly in some, well, with values we'll take in some bounded interval, sigma bar, low and high, plus some standard Lipschitz conditions in space, uniformly in time, okay? So this is our model. What do we have on the market? On the market we have some financial products that are called European options. What is that? Well, we fix a future time horizon, okay? You can think, of t equal 1 year or t equal 1 month. We fix a certain constant, k, positive. This is a price, so this is expressed in euros, okay? And we can buy a contract on the market that gives us this amount of money in the future. The maximum of k minus the future value of s, okay? So you can think, for those who have never seen this, you can think of this as an insurance product, right? You are protecting yourself against a drop or against a decrease in the value of s. You are thinking that s in the future will be very low, will go from 100 to 50, and if you have bought this contract, you will get some money, okay? Otherwise, if s is high, you will get 0, but, okay, so you're protecting yourself against drops in the values of the asset. Okay, so this we can rewrite in a simple way as positive part of k minus st. Okay, good. So the theory for pricing and managing these kind of products tell us that this object, okay, I'm buying the right of getting some money in the future, a capital T. I have to pay something now in order to have this right in the future, okay? So the price of this contract now, at time 0, is given by an expectation. Expectation of exponential minus RT, positive part, k minus xt, where x is another process. That satisfies this SD, where r, small r, is a constant that I'm introducing, positive. that represent the interest rate that you get if you invest money in a bank account, okay? So, we have to compute, and maybe we have an initial condition here that is the initial value as 0 that we observe over there, okay? So, the problem, the price is given an expectation. The problem we have is computing an expectation, okay? For which you can use, now the numerical problem we have is compute an expectation based on a stochastic process, solution of an SD, for which you can use your favorite numerical method, right? You can use Monte Carlo. In some situations, you can maybe compute this explicitly. This is an integral against the law of x. Or maybe you can solve a linear PDE that is satisfied by this expectation, right? Okay, so you can choose your numerical method, and maybe at this level, I'd like to point out that if we call this function, I'm not managing this blackboards very well. This function, we will call it P, TK, there's two parameters, T and K. P, you can think P stands for price. Actually, this is a put option, so it's the P for put option. It will depend on sigma as well, right? On the sigma that is inside my process. Okay, I'd like to point out that something that is known is this setting is that this function solves a certain PD. Solves the following PD. Okay, parabolic PD with an initial condition, P0k equal to, well, what you obtain when you inject t equals 0 there. Okay, so we have a forward PD, which is nothing but the Fokker-Planck PD for this process written in terms of the function P, okay? You can think of this, so there's many ways of proving this PD. You can think of it as the Fokker-Planck forward PD written in terms of the function P sigma. Okay? Good. So you can tackle the problem from the side that you want, and everything here is linear. Linear expectations, linear PDs. Okay, then we come to another type of product, which are this American option. I'm going to focus on during the talk. Okay, so we still fix a future time and some positive price k, okay? And this American option is a financial contract that still gives you some money in the future, okay? But you don't necessarily look at this difference, k minus s at final time. You can look at this at any time tau smaller than capital T, okay? So at any time tau, you can stop the game and you say, now I want to get this amount of money, okay? Which means that you exercise your option at tau. So this is what you get if you exercise your right at time tau smaller than capital T, okay? Okay, so again, the theory, which I'm not going to recall in details, but the theory for pricing and hedging, for pricing this kind of object, tell us that now the price I have to pay today in order to have this right in the future, okay, this is the American option. The price of this American option is not an expectation, but a supremum of expectation. Okay, it is, in the end, the value function of an optimal stopping problem. Okay, so it's the supremum of these expectations over what? Over all taus that belong to this space capital tau, that I denote in a standard way like that, which is the space of stopping times. in the augmented filtration of the Brownian motion W, okay, with values in 0t, in 0 capital T, okay? Okay, so we have this, yes?
So, just to remind you that perhaps you are using a different sigma from there to there because you changed that from the motivation that you have. Process S, you have the volatility sigma Ts of T, and then we use the same sigma. But it might not be the same function.
In which, what do you mean? So why might it not be the same function?
Because you have, in a certain sense, you are using you are transforming the x.
Sorry, maybe the yes. Okay, now please, yes, go. Yeah.
You're transforming the s to x, and your volatility at txt has to be changed from the sigma that you have at the top. You're changing variables, basically.
I'm changing variables, yes, but you agree that the price of this option is a number?
No, yeah.
That I can write in this way?
Yes, that's so far so good, but it's just that you're changing the processes there. But anyway, not a big deal.
But, okay, but you, okay, so we can discuss about that later, unless, so you agree with this identity and with this sigma?
I agree with the future.
Huh?
And I agree with the future.
Okay, very nice.
But the sigma in the x is the same as the sigma in the x.
Yes, it's the same, yes. This is what I mean, it's really the same, but...
Yeah, but the sigma in the p is just like a simple piece of sigma of tk.
Yes, this is a symbol. So this is an expectation that depends on a lot of things, on t, on k, on r, which I don't put, and it will depend also on the function sigma that I put there.
Yeah.
Okay. So, George, there's something I missed in what you said, I believe, but okay, if it's okay to go on like that, I would be happy to. So, yes, so now we have this problem to solve. Okay, let me make a small remark en passant, which I'm going to go back to afterwards. So you take in that problem tau equal capital T, okay, and what we get that this value, sorry again, this price now I will denote it as A tk, A for American, tk, and sigma, the function sigma is still there, okay. What we get is that A sigma tk is larger than this expectation computed at t. So this will be larger than what I call P, right? Just this expectation, the price of the European option, plus something, plus a certain amount that will be positive, okay? And this amount, this is what we call the early premium in mathematical finance, okay? Early premium because it's what you have to pay in addition to the previous price of the European option. It's the additional price that you have to pay if you want the additional right of exercising your option at any stopping time before capital T, okay? And I will go back to this formulation in the future, so in my talk, okay? So now the problem we have is to solve numerically. If we want to apply the model to market data, we have to solve numerically this problem over there, okay? Which is more complicated than just computing an expectation, okay? And so this is the moment when we wonder about efficient valuation numerical methods for optimal stopping problems, okay? Okay, so hopefully, quickly, I'd like to remind what are standard classes of methods to solve that optimal stopping problem, okay? Well, and now, from now on, I will start denoting UTX for T before capital T and X positive value. What? The value function of this optimal stopping problem, so the price of the American option, if I enter into the game at time small t. Okay? So it will be the supremum of these expectations. Okay, now taken over all stopping times, tau, that take values in small t, capital T. Okay, so I will use this notation, which should by now be clear. Supreme over all stopping times in the filtration of W that take values in the interval small t, capital T. Okay, and where with the standard notation again, x txs, right, is the solution of the ST starting at small x at time t. Okay, same notation as in a lot of previous talks. Okay, so this value function satisfies what we call a backward dynamic programming principle, okay, which is suitable for time discretization in such a way that we can actually simulate the random variables, right? So there's a backward dynamic programming principle, which, if we discretize time, okay, for which we can discretize time, we take n dates between 0 and capital T, regularly spaced, so tk k t over n, which means that I'm taking a fixed time grid, t over n. I can consider, and I know how to simulate, the Euler scheme for the process x, right? And so, what I can construct is a discrete time process u, starting from the beginning, from the end, sorry, okay, and then iterating backward from time ti plus 1 to time ti with this principle, okay. This will represent my gain at time ti. It is the maximum between, so the value of my option at time ti is the maximum between what I gain if I stop at ti and the conditional expectation of what I get if I wait one more step. And if I wait one more step, my value is uti plus 1. Conditional expectation with respect to my process at time ti. And I have to take the maximum between these two. Possibly I'm forgetting this exponential term here. Sorry. And I iterate from time n to time 0, okay? And then I will using the value u0 that I obtain as an approximation of the solution of my value function at time 0, okay? I forget the plus, yes, okay. Thank you, yes. Did I forget it? Everywhere, okay. Everywhere, yeah, thanks. Okay, so this now opens the way to Monte Carlo methods, right? Because the problem I'm left with is to simulate this conditional expectation, to which I can apply my favorite regression method, okay? Which means using the IID simulations of the Euler scheme against which to regress, and then choosing a basis of functions on which to project in order to replace this conditional expectation with a finite dimensional projection, okay? And we have heard about this in a lot of presentations during SEMRAX, for example, Plum and Turkidjev's, right? So this opened the ways to Monte Carlo methods, which are potentially applicable in higher dimension, okay? Which means that you have several processes, x1, x2, up to xd. But as I mentioned in the beginning, what I'm interested in now is the analytical counterpart of this problem in low dimension. And this is a free boundary PDE, okay, which is written in the following way, okay? So let me notice, first of all, that this value function over there is always larger than k minus x positive part, right? Just take tau equal small t, okay? It's always larger than this, which means that it can be larger, which can be strictly greater or equal, okay? So it makes sense to define this object, small x of t, this is a function of time, which is the infimum of point x, at which this function is strictly larger than, the value function is strictly larger than this fixed function, okay? And if we do this, the picture looks like that. If we do this, the picture looks like that. This is time, capital time, strike is here. Okay, this function x has this behavior. Okay, so this is small x of t. And I'm dividing the time-space domain in two regions. One in which my value function is larger than this, and one in which it is equal. Okay, so we can call this C, and this other one, we can call it D. Okay. So for the notation, capital X is the process, small x of t is the boundary. Okay. If you have complaints about this notation, I'd be happy to forward them to my co-author who chose it. So if we do this, then the statement is that u and this function of time x is the unique solution to the following problem. Okay, so in this region, what this identity is telling us is that it's optimal to stop immediately, right? If we look at this optimal stopping problem, utx equal k minus x means that tau equals small t is an optimal stopping time, right? So here it's optimal to stop immediately. Here it is not. Here it's optimal to wait a little bit before exercising, okay? So it makes sense that in this region, the value function satisfies the standard parabolic valuation PD. Okay, what we call C. While in the complement, we know that we have this identity. Okay. Up the other way around, sorry, yeah? Correct. And this we can call D bar, the closure of D, okay? The value function needs to be larger than the fixed payoff, okay? And then we have the final condition, the terminal condition, right? And maybe a boundary condition at infinity. This function has to tend to 0 at infinity, okay? Okay, so I'm looking at the couple, value function and this boundary as the solution of this problem, which is a free bound, which is what we call free boundary PD, okay? We're looking for the solution and this boundary at the same time. Okay, so this small x is, oh, by the way, L by L, you already imagined that, but this is the infinitesimal generator of the process x, so this will be Rx, first derivative, plus 1/2 second order term, okay? So this x, the boundary between these two regions, is what we call the exercise boundary of the American option. this x is what we call exercise boundary. Why? Because, well, the stopping time tau star, defined by the infimum of times at which I go below the level of this boundary, is optimal. Is optimal for the stopping problem, defining the value function, okay? So I start from here. If I start from 0, okay, the process diffuses, and this is the time, the first time it goes below this boundary, it's the time, the optimal time for stopping. Okay, so if we wonder about the properties of this function, okay, so a lot of properties are known. Because this function has been studied in several works, okay? In this setting, we know that this function is monotone. It is C1 over 0t open in t, and its limit at capital T is equal to k, okay? So it is really, it looks like the function I've drawn over there, okay? So this has been studied by a lot of authors. So by the way, this kind of system goes back to, the relation of this to the optimal stopping goes back to one of the usual suspects of this SEMRAX, okay? It goes back to works of McKean 65. And then properties of this exercise boundary have been studied by several authors between the 70s and nowadays, okay? Which I'm not going to quote so that I don't forget anyone. These are some properties that we know, okay? So what I like to use now is the fact that for this PDE, for this free boundary problem, we have an integral representation. We have an integral representation. Yes, yes. The boundary needs to be equal to -1. Yes, something I forgot. Yeah. Good point. Yes. This is something I forgot, so I will write it here. In addition, you want that the derivative in space of this function, we can write it like that. The limit from above is equal to -1, okay? So this, from below, in this region, we will have VTX equal to k minus x positive part, and this is actually equal to k minus x, okay? Because we are below k, so positive part, k minus x is positive, okay? So from below, the derivative of k minus x is -1, and indeed, a property that function u satisfies and that we need to ask in this system is that the first derivative in space is continuous while crossing the boundary. Okay, yes, thank you. So now going to what I'm calling integral representation. We can derive it in this way. We can derive it in this way. So what did we just wrote for the function u? We wrote that on the set C, the function u satisfies this equation, and that on D, well, which is an open set, for what I've just said on the function x, the same thing will be equal to, okay, on this set D, the function u is equal to k minus x, without positive part, because this is positive. So if we apply this operator to k minus x, time derivative 0. In L, there's a second derivative which hits a linear function, 0. So the only part I'm left with is Rx dx of this minus R k plus rx, right? So what we get, this is the most complicated computation of the whole talk. So what we get is minus rx plus rx minus rk, okay? On the region D, we have that this is a negative constant, okay? Good. So if we can write in one line the PDE, the equation satisfied by U. This is what? This is equal to 0 on C, and on D, this is equal to minus RK. So I can write, I take it to the other side, plus RK, indicator of what? Indicator of X in D, so X smaller than XT, right? I've written the two conditions in only one line, okay? But so we can see this as a linear PD for, well, a PD for U with a source term here, right? With a source term, which depends on T and X, well, and which is also a function of my exercise boundary that I will put there, okay? So we can see this this equation for the couple Ux as a non-linear equation, okay? Because X, the function X of T is there inside the indicator function. In any case, we have a Feynman-Katz representation for U, right? We have a Feynman-Katz representation for U from this PD that goes like that. Expectation of the terminal value, k minus x, plus what? Plus integral of the source term. So rk, here I have expectation of what? Well, here I have expectation of f of s xs, right? And so this is, according to my f, indicator function of xs smaller than the boundary, right? And I have to put initial condition here. Okay. And so, well, we can rewrite this in a shorter way that I will use, okay? So this is exactly the price of the European option, right? This is what I call P, capital TK, and now I'm changing notation a little bit. I don't put sigma anymore, I put the initial condition Tx over there, and then I have plus Rk integral of the CDF of the process, okay? Which I will write like that, where I'm introducing, okay, notation somehow standard for the CDF of the process. Okay, where my notation with F is the, as I said, the CDF, so probability that XS is smaller than Y if I start from Tx, okay? So here what we have just written is what we have identified is the early premium that I introduced before, right? So we are writing the price of the American option as the price of the European option plus a positive correction, okay, which is the early premium, and this is why we call this equation early premium formula. Okay, this is the early premium formula. Okay, so why is this interesting? Because now from this we can get rid of u in this equation and get an integral equation for the exercise boundary x. How? Just inject what? The fact that along this curve, the function u, which is a continuous function on my space-time domain, is equal to k k minus xt. Okay? So if we do that, and if we have colors, if we do that, well, we will obtain here k minus xt, right? And we will get xt here, and xs there, okay? So we have this equation plus the terminal condition x capital T equal k. This is giving me a way of numerically computing this exercise boundary, right? I start from the end, xt equal k, and then I discretize time exactly as we did before. We go from time tn to time tn minus 1, solving this nonlinear equation, okay, for xtn minus 1, okay? xtn minus 1, xtn minus 1, xtn minus 1, okay? And then we have, of course, to, discretize, approximate this integral in some way, okay? So this is, okay, so this is something that we can do provided that we know how to compute P and F, okay? This expectation and the CDF, which we know only specific cases, okay? Not in general. But so why is this interesting? For us, for me, for us. If we compute this exercise boundary, okay, then we can re-inject it into the equation, okay? We go back to the white, suppose we have computed x of t, we have evaluated x of t, we go back to the white equation, utx, ptx, ftx, xs is there, okay? But if I know, suppose that I know x of s, okay? Now, what is left to do, and I can compute f, what is left to do is to compute this integral, compute numerically this one-dimensional integral with respect to time with my favorite quadrature scheme, okay? This is a very simple task. So, we have nailed down the problem of solving the optimal stopping problem to computing a one-dimensional integral with respect to time, provided we know these functions, right? So, back to my issue. This expectation and this CDF, we know them explicitly only in specific situations. For example, when my process X is geometric linear motion, this will be written in terms of the Gaussian CDF. But I want to do it in my more general setting with a generic function sigma x, okay? And so this is the moment when we can call upon asymptotic calculus for diffusion processes, okay? And so, last part, in the time left, what can we work out for the asymptotics of the problem? Asymptotics in which sense? Asymptotics when time goes to 0, okay? So for this, I will consider a slightly simpler setting for the presentation, which is a function sigma that does not depend on time. A function sigma that does not depend on time, okay, only sigma of x, which is of course a limitation that we don't want to have in practice, but okay, I'll consider this setting in the presentation, okay? So what we know about this exercise boundary x is that it tends to k, okay? What we want to know is more. We want to have a whole asymptotic expansion of x t as t goes to capital T, okay? Which means that for this function here that I drew, we want to know how it behaves here, okay? We want to refine what is known on its asymptotic behavior, okay? So to this end, I will just denote, okay, let me notice that xt is a homogeneous Markov process, okay? So I can denote, I can reverse time. I can reverse time and denote u bar, okay? U bar tau of x as the value function in terms of time to maturity. This will be u of t minus tau x, okay? For any t, for any capital T, okay? And the same for the exercise boundary. The same for the exercise boundary, so it will denote x bar of tau, the exercise boundary as a function of time to maturity. Okay, so what we know now is that x bar of tau tends to k as tau tends to 0, okay? We are sending, tau now is no more a stopping time now, of course. We're just sending time to maturity to 0. Okay, so our contribution in this setting with my collaborator, by the way, Pierre-Henri Labordère, whom I haven't mentioned yet. Our contribution is done in 2 steps. So step 1 is to derive an alternative representation for the exercise boundary. Okay. Which is written in terms of what? In terms of the density, the transition density of my process. Okay, so I will denote, if you forgive me for introducing notation now, I will denote f of t y x. This should be readable. The transition density of the process from point x to point y in time t. Homogeneous Markov process, we only have a time lapse. Okay, so in symbols, this is this low, right? So the alternative representation that we have is the following. I will write it. Okay, so the density, the transition density of my process from x bar tau to k equal to okay, well, equal to, I maybe forgot some exponentials before in the Feynman-Katz representation. I believe I forgot this exponential in the integral term, but okay, let's say it's not such a big deal. Integral of the density computed at this point. Okay, so okay, so what we have, this exercise boundary here, 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 and its derivative, okay? So the picture would be like that, t minus tau. Okay, we have an equation that involves this value, x bar of tau, and we are looking at the transition of the process from x bar of tau to k here. And here we have an integral functional that depends on the density of the process computed along this transition density along this curve, okay? So you might say, earlier we had this early premium formula written in terms of expectations, right? Put price and CDF. Now I manipulate it in such a way that I might prove, but I probably won't. And we manipulate it in such a way that we write it as an equivalent actual representation that makes the density of the process appear, okay? Good. So what did I gain? Okay, what did I gain? Well, what we gained is the fact that now to this representation, I can apply step 2, which is using what we know on the asymptotic behavior of the density of the process as time goes to 0, right? So now we open the way to decades of literature about heat kernel expansions in small time. right? And in particular, what we know in this simple one-dimensional case is that the density of the process looks like that. There is an exponential term, okay, which depends on x, y, over tau, okay? For Brownian motion, this d would be x minus y squared. D would be x minus y, sorry. I'm not finished, okay? But just let me point out what d is. This d square is, okay, in a fancy way, it is the squared geodesic distance of x to y in the Riemannian metric induced by the function sigma, okay? Which means what? This is a Riemannian distance, so it is the infimum of lengths of curves which are integral from 0 to 1 of phi dot t divided by my sigma phi square. The infimum computed over all the phi that are, well, in Cameron-Martin space of Brownian motion, H1, okay, absolutely continuous with L2 first derivative, and that connect x to y. Okay, so this is really a distance, right? You look at all the curves that go from x to y, and you compute the one that has you consider the one that has minimum distance according to this metric, okay? But then in a much simpler way, in this one-dimensional setting, this function d xy is actually just equal to the integral from x to y of 1 over sigma, okay? Okay, which is an easier way of looking at it. Okay, so this function, we know it, and then there's something in front, okay? A one-dimensional diffusion has a time scale that is square root of tau, okay? And then we have a coefficient in front, which is precisely this, okay? Well, so a certain coefficient depending on sigma, divided by sigma y 3/2, why not? Sorry for that. 1 plus big O of tau, okay? So this is an exact expansion for the density of the process. And now what you do is to inject this into my new integral representation, okay? So you do this, you inject this expression, and now the problem you are left with is the problem of working out the asymptotic expansion of x as tau goes to 0, the asymptotic expansion of x from the explicit asymptotic expansion of the density f, okay? So you are left with the problem of asymptotic analysis, which is maybe not a piece of cake. I mean, in which, in particular, you will need to use Laplace method to study the asymptotic of this integral, okay? But so you're left with that, and conclusion, you obtain an asymptotic expansion of this function, okay? Of this function here, which refines which you can push a priori to arbitrary order, which refines the expansions for the exercise boundary that were known in the literature, okay? I think I will stop in 1 minute. So you obtain an explicit, so the message that you obtain an explicit approximation for this function. You re-inject this function into the early planium formula that we had before, and you have a semi-closed approximation as a final result for the price of the American option. So for the solution of this optimal stopping problem, okay? The numerical, which is, of course, very accurate, right? And the numerical results of which you can look in my slides, which will be online, which I wanted to show you, but I think it's better to stop because it's 11. Okay, thank you very much.
Thank you very much, Stefano. Is there any question?
Just can you recall where does your last representation come from? This one.
Yes, this one. So it really, in a nutshell, you basically you start from the early premium formula for the original early premium formula for this function, okay? So here we have what? We have this plus I'm changing time, okay, I'm making some time change, so we have this. Okay, up. Take derivative with respect to tau, okay? You will have derivative with respect to maturity of the put price, okay? Then the derivative with respect to time with tau will hit here and hit here. Apply Dupier's PDE, apply Dupier's PDE. This term, as you can see, will pop up from Dupier's PDE, right? This is the second order term in Dupier's PDE. And what you're left with is still the integral term that you have when you differentiate with respect to tau. You see you have to differentiate here. The density comes from the derivative of the CDF, and then you have this derivative that appears. Okay.
Okay.
So this step is simple. This step is simple. Okay.
Okay.
What is more involved is than the second one.
Thank you.
Yes, please.
Of course, it's possible to develop this expansion more, and you have only the big old tau term.
Yeah.
But of course, you can make a complete series for this expansion, and if you inject this complete series expansion in the integral formula, then could you handle this? Maybe taking more terms.
So potentially yes. Then what we noticed is that actually the asymptotic of the exercise boundary, you know, here this function behaves as what, k minus sigma k times square root of tau log of gamma over tau, okay? So it has a behavior, almost square root behavior in tau times log of 1 over tau, okay? This is what pops up. And actually this and the further refinements here only depend on what is here. So they don't depend because there's square root of tau, the square root of tau, so all the terms that come from here, okay, that comes from this big O of tau, let's say heuristically, these terms, they don't count in the, so I don't know, I don't need this.
Any more question?
But if you have a kind of integral equation, yes, for your boundary, so you can apply kind of method to solve this equation. For example, you can kind of Picard iteration, something like this. Why do you need this asymptotic result?
Of course, as you say, we could apply methods for this integral equation for this one or for the original one. Okay, for this one, if we know the density. So we could, of course, we could. What our aim was to obtain these explicit formulas for the exercise boundary, in the sense that at the end, you know, you plug in this formula, in the end, globally, what you have is an almost explicit formula for an American option. Right? The only numerical task left is to compute this integral with respect to time, okay? So for calibration, what we have in mind is calibration purposes that I haven't mentioned here. But okay, so as usual, right? You want semi-closed formulas to have faster computations, and so our aim was really to work out an explicit formula rather than a numerical solution of this equation. I don't know if this answers to...
Yeah, but I mean, explicit is only up to this error.
Yes.
If your options are not short maturity options,
of course. If the options are not short maturity, this will worsen, the quality of the approximation will worsen. American options typically have maturities no longer than 1.5 or 2 years, for which we tested our approximation, and of course it works very well.
Usually in the market you have not American but discrete time American.
You have discrete time American, so you mean Bermudan? Okay, yeah, fair enough. Then either we just assume that our Bermudan are American, or Well, yes, of course. For discrete time American option, this will change. Yeah.
Okay, let's thank Stefano once again.